So in the sixth homework set, what I suggest you do is compute the matrix element of Z between the 3-1-0 state and the 1-0-0 state of hydrogen, and then use that later to compute the partial lifetime of the 3-1-0 state to the ground state, or the partial lifetime. In other words, the transition rate from 3-1-0 to the ground state. 1 over that gives you the lifetime if the warrant of 2s state. And so that's an upper bound on the lifetime of the 3-1-0 state. Well, the thing is obviously spherically symmetric. So it's an upper bound on the lifetime of all of 3-1 states. So today I want to do spontaneous emission from the 2-1-0 state, and that'll be a calculation you can imitate to do the sixth homework assignment, at least the first two problems of the sixth homework assignment. And so then at this time, I'll start the ionization of atomic hydrogen, ground state, in its ground state. Okay. So a spontaneous emission, remember that LF is Li plus or minus 1 because of angular momentum and parity in the dipole proximity. More generally, in the other rates that are about 1,000,000 times slower, remember k dot x is 1 over 1,000, but it gets squared. So when you square it, it's 1 over 1,000,000. And the other one is, well, MF is equal to MI if you use Z as the matrix element. Otherwise, it's MI or MI plus or minus 1. So those are the selection rules in the dipole approximation. And we're starting with the state 2, 1, and just for simplicity, I'm taking 0 as the state. And that's going to go to the ground state 1, 0, 0, and a photon of momentum k. So that's the transition. And remember, where both of these are eigenstates of H0m plus H0 field, the matter and the field Hamiltonian. Although actually part of the matter Hamiltonian is actually the scalar part of the scalar potential part of the field Hamiltonian. That is to say, the E squared longitudinal, because of Gauss's law and the Coulomb gauge condition, gets turned into the E minus E squared over R. So what we're computing here for 1, 0, 0, k, S of t is 0, 2, 1, 0. This thing, as usual, is minus I over h bar, integral 0 to t, and then it's 1, 0, 0, k, e to the I, h0m plus h0f t prime over h bar. The potential is minus 2 over m, a of x and 0 dot p. And then, wow, big typo here. Big typo. Minus I, h0m plus h0f t prime over h bar dt prime. So I somehow left this factor out in the just to remind me myself where this typo is on the paper kind of notes. All right, so that's the expression, and of course the field A of x and 0, this is the transverse field in the Coulomb gauge. It's the sum of momenta, which are box quantiles and polarization. There are only two left in the Coulomb gauge. There's a fudge factor, which is the square root of h bar over 2 epsilon 0 d omega k to the 1/2. And then we have epsilon r of k, a sub r of k, e to the I k dot x, plus epsilon sub r star of k, a sub r dagger of k, e to the minus I k dot x. Okay, so that's the computation there. I think the one way of systematizing these things is to call this thing f for fudge factor. Of course, it's a lot more than fudge factor. It's actually a computed quantity rather than a parameter. But it might simplify the calculation by using that abbreviation. Now remember, the annihilation creation operator is such that the matrix element, this matrix element is delta r, r prime, delta k, k prime, and it's Kronecker delta because we have box quantization. Otherwise it would be a delta cube of k minus k prime. And, wow, this typo propagates. It's really terrible. No, it doesn't. The next line. Okay. So, taking advantage of the fact that these states are eigenstates of these Hamiltonians, what we get is that 1, 0, 0, k, st0, 1, 0, 2, 1, 0 is, well, I have 2, 1, m actually in the calculation. Maybe I should leave it as 2, 1, m. It clearly doesn't make any difference because the ground state is wow, here's a typo. There's a 2, 1, m state here. 2, 1, m. Okay, so then this is IQ over h bar m, and maybe I'll use that abbreviation, f, for that square root, and then go e to the I e1 plus h bar omega minus e2 t prime over h bar 0 to t, and then the matrix element 1, 0, 0 epsilon r star dot p e to the minus I k dot x 2, 1 m t prime. I should have and could have factored this matrix element out of the integral because it's obviously not time dependent once one factors out this exponential. And so this thing is then, when we do the integral, you get an I over h bar in the denominator, which cancels this I over h bar. So this thing is q over m times this factor f. Then the matrix element 1, 0, 0 er star dot p e to the minus I k dot x 2, 1 m. And then this integral over time gives us just e to the I e1 plus h bar omega minus e2 t minus 1, all that over e1 plus h bar omega minus e2. Okay, so that's the whole expression. The probability is the square of this thing. And so that's Q over Q squared over N squared, F squared, the matrix element squared. This is another typo here. Notice that because this matrix element is squared, this always happens in quantum mechanics, the amplitude is squared, you get a probability. That means the coupling constants here come in as the square, and the dipole approximation terms come in as the square. And so that's what makes the dipole approximation so good. And that also is what makes quantum electrodynamics so accurate, because the coupling constant's effectively 1 over 137. Well, I should say the square of the coupling constant is 1 over 137. And so the power series of that, you pretty soon get very good accuracy.
Where did the epsilon r term go? There, I see you have the epsilon r star. And I was wondering.
This one here.
Yeah. Nope. The back, right there. That one is missing from your next statement. Is it because
this is epsilon sub r of k, and this is epsilon r of star.
Right. So epsilon r star is up there.
Yeah.
And I don't see epsilon r. And I'm assuming it's because of A.
Oh,
so
it's because you see this thing. All of this is part of A. A sits between a state of 1 photon here and a state of 0 photons there. So the only operator that survives is the creation operator, the one that creates the photon. The annihilation operator would act on the vacuum and just give you 0.
Okay.
Good question. I'm running out of chocolate, but I've got 3 left, so I can probably be solvent during this lecture. Okay, so the rest of this, I haven't finished writing down the probability. We've got that, and then we have this thing. If you multiply it by half of the space, by this the square root of the space factor, you get a sine times 2i. When you square it, you get a factor of 4. Sine squared e1 plus h bar omega minus e2 divided by 2h bar. It's a half angle. And then you have that divided by the square of the energy denominator. Okay. And remember, we have our magic delta function formula, which says that this part here that the limit as t goes to infinity of the stuff in curly brackets, well, without the 4 actually. Nice. So let me put a 4 actually. With the stuff in curly brackets is pi t over 2h bar delta of the energy miss, the difference between the initial and final state's energy. The initial state energy being E2, the final state energy being E1 atomic plus h bar omega for the emitted photon. Okay, so when we make that substitution, we get an expression for the rate, which we then have to multiply by the density of final states and sum over those final states. So what we get then is that the rate is the time derivative of increase in the probability, and there are a couple of 2's in the denominator, and I'm going to have to abandon my half business now and just go to pi q squared over m squared epsilon 0 v omega k, a matrix element squared and in fact I could have skipped a step because the next thing is just to use this rule for to turn the square of the electric charge into the fine structure constant alpha, which is 1 over 137, h bar and c, 4 pi, and epsilon 0. And so that gets us into, well, we were in SI units, but it sort of keeps us there. Anyway, so W hat then is 4 pi squared alpha h bar c over m squared v omega k. This is the energy of the final photon. 1, 0, 0. Epsilon star r k, not v. Okay, so that's the expression. And now what we do is, of course, we say, well, remember as when we did the absorption of a photon, P we can rewrite as m over I h bar times the commutator of x with h0 matter, and that would be a step backwards, but we've got eigenstates of h0 matter on both sides of this matrix element, and once again, that wouldn't be much help, but we're going to make the dipole approximation and replace e to the I e minus I k dot x just by 1, and that means that so in other words, we're also going to say e to the minus I k dot x is equal to 1. That would be a laughable approximation if it weren't for the fact that we're talking about optical photons and atoms. In the next topic, when we discuss the ionization of hydrogen, we're not going to be able to make the dipole approximation because the photon is going to have to be higher in energy, at least 13.6 eV, and possibly higher. That's going to kick it into one of the way up into the continuum. And in that case, e to the I k dot x doesn't work. And moreover, it also isn't going to work in that case because the final state, although the initial state is 1, 0, 0, the final state is a plane wave. It's an electron going out. All right, in any event, after we've made these two approximations, then what we can say is that W hat is 4 pi squared alpha h bar c over m squared v omega k 1, 0, 0 m over I h bar epsilon star of k dot x commutator h0m to 1m. Of course, replacing p by this isn't an approximation, but dropping the rest of the dipole approximation certainly is. Okay. So, well, I forgot the delta function. Okay, well, this delta function is going to enforce energy conservation, and but before I get to that, let's just pull this out. We're going to pull out the m and the IH bar, which becomes n squared, canceling this m squared, and then an h bar squared down here. And then it's going to give us, to the right, it's going to be E2, to the left E1, so it's going to give us E2 minus E1. And so that tells us then that W hat is 4 pi squared alpha C over H bar of B omega K E2 minus E1 squared 1, 0, 0 epsilon r star dot x 2, 1m squared, and then delta E1 plus omega minus E2. Okay, now this delta function acts to ensure that omega k is the same as E2 minus E1. And so what we can do is simply cancel the E2, one of the E2 minus E1s and the omega, and that gives us a slightly simpler. Okay, well that's going to be our final formula for the moment. What we're going to do now is look at the matrix element, and now, as I said before at the beginning of the hour, this initial state here, well, the final state is a photon going out in some direction, and the 2,1m, we can choose our coordinate system. We're going to choose our coordinate system so that the initial state has m equal to 0. And so that amounts to a coordinate system choice. So that'll be the z-axis, and everything else will follow from that. Now we want to compute what this 210 is. And for that, we're going to use a couple of formulas, namely R10 of R is 2 over A0 to the 3 halves. EB minus R over A0, and R21 of R is 1 over root 3, 1 over 2A0 to the 3 halves, R over A0, e to the minus R over 2A0. I suppose it would have been more attractive to put a 2 here and a 2 there. Also, the angular part here is y00, which is 1 over the square root of 4 pi. And the angular part here, we'll write it down here, y10 is square root of 3 over 4 pi cosine theta. So, to find this matrix element, then, if this thing is a 0, then the only part that survives here is the z component. The reason for that is that This is invariant under rotations about z. This is invariant under rotations about z. So if you have an x or a y here, you can rotate it around x into minus x, y into minus y. Okay. So the only thing that survives is z. Is that clear, or do you want me to show it more carefully? All right, so only the z component survives. So what we've got then is we need to compute. In other words, we can say 1, 0, 0, epsilon r star of k dot x 2, 1, 0 is equal to epsilon sub r star of k sub 3 times 1, 0, 0 z 2, 1, 0. And now we can just compute this. And so we have, whoops, that's a 1. 1, 0, 0, z, 2, 1, 0 is an integral of the omega integral 0 to infinity r squared dr. And then we have the 1, 0 wave function which is 2 over a0 to the 3 halves e minus r over a0 divided by square root of 4 pi. Then z is r cosine theta. And then the R21 is e to the minus r over 2a0 divided by root 3 2a0 to the 3 halves r over a0 square root of 3 over 4 pi cosine theta. And I think I've got everything in there. Okay. If you do the d phi integration, you get a 2 pi. So you wind up with a 2 pi over 4 pi. 1 over the 0 being the Bohr radius, so 4 root 2 minus 1 to 1 d cosine theta 0 to infinity dr r to the 4 e to the minus 3r over 2a0 cosine squared theta. If you do the angular integration, you get 1 over 3 root 2, 1 over a0 to 4 equals 0 to infinity dr r to the 4 e to the minus 3r over 2a0. These integrals are all well-known tabulated integrals, and so altogether we get 1 over 3 root 2 a0 to the 4 factorial over 3 divided by 2a0 to the 5th power, which turns out to be 2 to the 7th over 3 to the 5th root 2, so I guess I could have said 2 to the 7.5 times a0, or a nicer way of writing it would be 2 to the 7th over 3 to the 5th root 2 h bar over alpha mc. So this h bar over alpha mc, if I recall correctly, is the quantum wavelength of the electron, and then it's increased by a factor of 137. That gives you the Bohr radius a0, which is 0.53 angstroms, a little more than half an angstrom. Any questions? All right, so we now take this value for the matrix element and we stick it in here, and we've got this expression. And so we substitute in, wonder what if I just skip a step here. All right, let me skip a step. So we get W hat as 2 to the 17th over 3 to the 10th. What's happening, of course, is that we're squaring the matrix element. That's why we get these extraordinary powers. Pi squared h bar squared over alpha c m squared e2 minus e1 over the volume of quantization epsilon sub r of k sub 3 absolute value squared, and then this final state delta function e1 to the 2 bar omega minus e2. All right, now, remember I warned you that in doing this problem, it was pretty much just a straightforward application of the techniques that we had already seen until we get to discussion of the polarization vector. And here at this point, we no longer can just turn a crank. We actually have to think. And so this always causes something of a crisis. So what do we have here? The sum, basically we have a space here, R3, of polarization vectors, and they're spanned by epsilon 1, epsilon 2, and then we've got this third direction is the direction k. And this is easiest to think about if we imagine that all the polarization vectors are real, then you have these two vectors and then that vector. In any case, what we have is the sum r equals 1 to 2 of epsilon r of k. This is an outer product. Epsilon r dagger of k is going to be the 3 by 3 identity matrix minus the outer product of k with k transpose, or k dagger if you want, but k is real. Okay, so that's the expression for the sum of the polarization vectors. What we want is the 3-3 component of this. So the 3-3 component of this matrix element is, of course, 1 from the identity matrix minus k3 squared. And I should have said k hat 3 squared. And we took the z-axis such that that our state was in the m equals 0 state, and the initial state. And so this photon then is coming out at some arbitrary angle, and this then is 1 minus cosine squared of theta, where theta is the angle of the final state photon relative to the z-axis, about which the initial state atom has m equals 0. Okay, we now have to sum over the momentum and spins of the emitted photon, and as usual, we've done box quantization. K is 2 pi over L, a vector of integers, positive or negative, the vector of integers then is L over 2 pi vector k. And so a sum over the vector, over the integers is L over 2 pi cubed integral d cubed k, which is to say volume integral d cubed k over 2 pi cubed. And so now that's what we've got to do with this. So when we sum over the polarizations, we get 1 minus cosine squared theta for this term here, and then we have to integrate the rest of it d cubed k and multiply by v. So, I guess blackboard-wise, I'll go over here. So what about a question? All right. So now the full rate then, the full transition rate is 2 to the 17th over 3 to the 10th pi squared h bar squared e2 minus e1 over alpha c m squared integral d cubed k over 2 pi 3. This is the sum of the pi squares. 1 minus cosine squared theta from the sum of polarizations. And now just delta of E2 or E1 plus h bar omega minus E2 and so this is the same thing here, and then what I'm going to do is I'm going to take this dk integration, write it as k squared. And remember, dk, well, if we multiply by c and h bar, this thing is d h bar omega, and so to compensate we have to divide by h bar c. And so I'm going to write, instead of dk, I'm going to write dh bar omega and compensate with an h bar c, integrating 0 to infinity. The integration over phi, the azimuth angle, is canceled 1 over the 2 pi, and the rest of the cosine integration is dx over 2 pi squared 1 minus x squared. And then we still have this delta function. So that's our expression. Now this, since we're integrating dh bar omega, this just says that h bar omega is e2 minus e1. And so that means that this k is therefore k is omega over c, and h bar omega over h bar c, and so squared is that squared, which is to say e2 minus e1 squared over h bar squared c squared. So that's the delta function sets k squared into this. And so altogether then, what we have is 2 to the 15th over 3 to the 10th. H bar e2 minus e1 over alpha c squared m squared, and then e2 minus e1 squared over h bar squared mc squared, and then this integration dx 1 minus x squared minus 1, which in fact is just 4/3. So what we finally get is, if we put what we finally get, let me just write it this way, we wind up with 2 to the 17th over 3 to the 11th, e2 minus e1, that's from the 4/3, cubed over alpha h bar c to the 4 n squared. Okay. So that basically is our final formula for the transition rate. But of course, we can compute E2 minus E1 because we know what the levels are of atomic hydrogen. And I know the energy levels, again, are minus a half mc squared alpha squared over n squared. Or again, alpha is 137.036, I think. All right, so then E2 minus E1 turns out to be 3/8 mc squared alpha squared. And that gives us a final formula for the rate, namely, well, our penalty variable, 2 to the 17th over 3 to the 11th, 3 cubed over 2 to the 9th, m cubed c6, alpha to the 6th, over alpha h bar c to the 4 m squared. And as you've no doubt noticed, there are ample opportunities for cancellations. And when we do the cancellations, we get 2/3 to the 8th power mc squared alpha to the 5th over h bar. Now, the thing that has struck me repeatedly over the last half hour as I was writing these expressions is how, because the system is quantized and because the hydrogen atom has not only spherical symmetry but also a hidden symmetry, so it has an extra symmetry. The formulas are particularly simple. They involve prime numbers to integer powers, and then a combination of fundamental constants that is the only one that I suppose you could have that would have the right dimensions. Maybe I'm wrong about that. And then an appropriate number of fine structure constants. And so it's just remarkably simple that symmetry and quantization have given us such a simple result. The lifetime then, tau, is 1 over the transition rate, and this then is 3/2 to the 8th h bar over mc squared alpha to the 5th. And if you put in the numbers, roughly speaking, mc squared is 0.511 MeV, so it's roughly half an MeV. H bar is 6.582 times 10 to the minus 22 MeV seconds, and alpha is 1 over 137.036. And so now if you put those together, you get a number that's very close to 1.6 nanoseconds. And so we get tau is equal to 1.6 10 to the minus 9. And notice that this is the experimental lifetime. Too high accuracy because the other, the corrections to the dipole approximation would be down there quite low. There might be an interference term which would bring them up to 1 part per thousand. Otherwise, they're 1 part in a million. Let me say a couple more things, though, about corrections to the dipole approximation. If you take the next term, actually, no, never mind. In our case, it's e minus I k dot x because we were talking about creating a photon. And this is 1 minus I k dot x plus dot dot. So you keep this term. And this is something that you need to do if the original state was 2, instead of 210, if it was 200, if you were trying to do this transition. Okay, the k of the 2s state. Clearly the 2s state is going to be a longer lifetime. And the reason is that this term is 0, and so it has to go through this term. And so this is slowed down by a fact, the amplitude is slowed down by 10 to the third, 10 to the minus 3. And then the probability is slowed down by 10 to the minus 6, so the lifetime is up by 1,000,000. So these the lifetime then of the 2s state must be of the order of milliseconds, or the order of a millisecond, maybe 2. And the transitions from the 2s to the 1s, there are 2 kinds of transitions. One is magnetic dipole, and the other one is electric quadrupole. And this is according to whether you have the antisymmetric or the symmetric part of the matrix element. Remember, the matrix element would be 1, 0, 0, epsilon cigar of k, say, star, dot x times k dot x, 2, 0, 0. And so if you have, so you can see that there's an xi, xj time gets multiplied by epsilon r star and k ij, and you can separate that quantity out into an antisymmetric and a symmetric part. And if the antisymmetric part is contributing, then it's magnetic dipole, otherwise the electric quadrupole. And in any event, these are slower, much slower transition. It's still too fast to see with the naked eye. All right, well, the next topic then is the ionization of atomic hydrogen, but if there are questions, we can start with we can ask the questions of the questions. All right. Okay, so the next topic is ionization of atomic hydrogen. And remember, H0m is P squared over 2m minus E squared over R. And in fact, that's actually true as long as we think of E squared as alpha H bar C. That's a way of writing it. Now the final state is going to be Pf, which causes H bar Kf. So this is the final state electron. And we can write this final state electron as its plane wave. X Kf is e to the I x dot Kf over square root of b. So here it's normalized. And the advantage of using K is that it has the 1 over H bar in it, so we don't have to write T over H bar. And as usual, K is 2 pi over L. Vector of integers N, and V is going to be L cubed. So once again, now what is our final state? Our final state is just simply case of F. And then we have our S operator, and the initial state is 1, 0, 0, and some photon, K. Now I see a blackboard bordering problem. This is then minus I over H bar, integral 0 to T, K final, E to the I, H0 matter plus H0 field, T prime over H bar, then minus Q over M, A dot P, E minus I, H0M plus H0F, T prime over H bar, 1, 0, 0, K, Okay, so that's our expression. And again, once again, the initial and final states are eigenstates of these, of the, what we call the free Hamiltonians. And so what we've got is then IQ over H bar M. I'm going to take the matrix element out now. It's going to be Kf A dot, well, let me not try to do everything at once. A dot P 1, 0, 0 K. So we can pull that out of the time integral. And then the time integral is integral 0 to T of e to the I, and then what we're going to have is let's see, well, I've got this EF. Okay, so we've got EF minus E1 minus H bar omega. T prime over H bar dt prime. Okay, so that's our computation. And so the remainder of computation, we know how to handle this. This integrates to the phase factor minus 1 divided by the energy denominator. We use our magic delta function formula to turn that into a delta function and a couple of constants, and so we have to compute what this is. And we use our same old formula for the electric field. Here the annihilation operator will come in. But here we're not going to use the trick that we used before, writing P as the commutator of X with H0M. Instead, P, this final state is an eigenstate of P. And of course, A and P commute. And so that's just going to give us a KF dotted into. All right, so let me write this here then. In other words, Kf A dot P 100 K. What is this going to be? Well, there's going to be this fudge factor. Actually, call it a fudge factor. 2 epsilon 0 b omega k to the 1/2. Then there's going to be k final dot epsilon r of k. And now what's left is k final. The annihilation operator turns this into vacuum with just a factor of 1. And so the final factor here is EDI k dot x times 100. I don't think I've left anything out at this point. This is the operator here. This k is the k of the initial photon. That's that k. And right, so that's the k of the initial photon. All right. So, see, I'm having to translate from my notes are in unrenormalized Heaviside Lorentz units. Okay, so what is our transition rate then? It's, when we do the integral, the IH bar cancels. So we get Q over M. We get all of that, which is H bar over 2 epsilon 0 b omega k to the 1/2. We have kf dot epsilon r. I'm just going to leave it like that. And then we have kf EDI k dot x 100. We still have to compute this matrix element. Then we have this phase factor e to the I EF minus H bar omega minus E1 T over H bar minus 1 close parentheses over EF minus H bar omega minus E1. And when we take the square of that thing, that's going to kick out a factor of 4, and then it's going to be a sine squared over an energy denominator squared. So P of T is going to be Q squared over M squared H bar over 2 epsilon 0 b omega k kf dot epsilon r absolute value squared, this matrix element absolute value squared. There's a 4 kicked out from there, and then we have sine squared of EF minus H bar omega minus E1 T over 2H bar divided by the square of the energy denominator. So that's our probability. Everything, we know everything about it except for this thing, which we have to compute, and then of course we have to use our magic formula, namely that in the limit, this thing turns into pi t over 2h bar, delta function of the difference of the energies. Okay, so By the way, why don't you send me email on what you want to see next? I think this is, for me, when I was a graduate student, let's say, the high point of the quantum mechanics course was calculations like this, which occurred in the spring. And so I can continue with these. In fact, what we could do is quantize the field of the electron and do, say, Compton scattering, which is the scattering of the photon off an electron, and do pair creation and a couple of some other calculations. But I don't know, maybe you guys, and maybe do the Casimir effect, maybe you guys want to see something else though. So why don't you send me email saying what topics you prefer to see covered. Let me get a drink. By the way, I was reading last night. See, in fact, reading Jean-Claude Deals quite correctly. He was complaining about the export controls, and that reminded me that Oppenheimer had made fun of export controls in the summer of 1949, and in fact, Oppenheimer couldn't resist making fun of people. Making fun of people, and he was extremely good at it. And there was this guy Strauss, who was a very powerful politician, and he was pushing export controls on nuclear isotopes. And so Oppenheimer said, well, you know, this is an ambiguous thing. You can use anything to make a nuclear weapon. You can use a shuttle to make a nuclear weapon, and we did. You can use a bottle of beer to make a nuclear weapon, and we did. In as much as they use shovels and beer and at Los Alamos. And then he went on to say, as we get to the issue of simply nuclear isotopes, I would say, well, that they're less important than, say, electrical devices, but more important than vitamins, somewhere in between. Maybe that's hysterical. I didn't suppose people laugh, but Strauss was really annoyed, and he then used his political power to ruin Oppenheimer. And my impression is that Teller was a pawn in that illumination. He might have been a willing pawn, I don't know. The person behind it was not Teller, it was Strauss. Largely because Oppenheimer made fun of him in these public hearings so effectively. All right, well, here is our expression. And we only have a tiny bit of time left in this hour. Let me just sketch how we'll do this, and then we'll come back to this calculation at this point. This matrix element, K sub F, EBI K dot X, 1, 0, 0. Well, this thing, so I've got all these different notes. Okay. What we're going to do is we're going to write that as integral d cubed x, and then we're going to put in here kf. We're going to insert a complete set of x states, EBI K dot x, 1 state 1, 0, 0. And so this is integral d cubed x. This thing here is e to the I kf dot x. Actually, it's e to the minus I kf dot x, and the normalization square root of v. And then we have e to the I k dot x. This is the incident photon. And then we have r10 of r, effectively, over square root of 4pi. So that's the way one does the calculation. And so you see, we're not making the dipole approximation. The dipole approximation, we replace this by 1. Instead, we treat this part of the thing exactly. And that amounts to taking the Fourier transform of the ground state wave function of hydrogen. And so we'll continue that next time. I think that's about where we need to stop. Does somebody have a pencil so I can make a note?